Now that we've set up the idea of normalization, we're going to look at how we solve the problem of the quantum mechanics of a particle in a box. As I said, this is perhaps the simplest problem in quantum mechanics. It also turns out to be directly a very useful one. And it shows the main features of a whole class of problems, which we could call energy eigenproblems. Specifically, we can introduce the idea of quantization and of energy eigenvalues and the eigenfunctions that go along with those. The kind of results we get for these are quite characteristics of quantum mechanics in general, both in their form and in the magnitudes of results that we get. As we work with nanostructures, for example, tiny little things on nanometer scales, we encounter many situations in which this particle in a box is actually quite a good first approximation to the behavior of quite real quantum mechanical systems.
So we will consider a particle of mass m, and we're going to presume that there's some potential v of z that varies in the z direction. And so we will have a Schrodinger equation just like we have drawn before. And E here will be the energy of the particle. And of course, psi of z is the wave function. So suppose then specifically that the potential energy V of z is this rectangular well. So we imagine, as it were, that we're falling into a well here. We call this a rectangular potential well. And of course, what we're showing in the vertical direction is the energy, and in the horizontal direction, we're just showing position in the z direction. Specifically, we'll choose a thickness, Lz, and we'll choose the energy origin, the potential energy origin, to be 0 at the bottom of this well. Now, it does not matter what we choose for this energy. We'll get the same actual physical results in the end. And so we can choose it to be anything we want that is convenient for our algebra, so we'll choose it to be 0. And then at the walls, we imagine that the potential energy would rise up towards infinity. So at z equals 0 and z equals Lz, the potential rises up to infinity. And sometimes we'll call this potential well structure here an infinite or an infinitely deep potential well, or just an infinitely deep well. Now, because these potentials at z equals 0 and z equals Lz are infinitely high, but we presume in the end that the solutions we're looking for correspond to finite energy, then we presume there's really no possibility that we would find the particle out here. At least we'll take that presumption. So for z less than 0 or z greater than Lz, we presume the wave function is going to be 0. So it's going to be 0 out here, and it's going to be 0 out there, because we don't think there's any probability that we would find the particle out here. And so we reasonably assert that the wave function should also hit 0 at the walls. This is just an assertion we're making, but we're going to assert that. So with these choices inside the well, that is inside here, our Schrodinger equation is going to simplify a bit because the potential V we've chosen to be 0 in there. And so the equation becomes a simpler version here, with the boundary conditions that psi of 0, that is at this point here, is going to be 0, and psi of Lz, that is at this point here, is going to be 0. Well, the general solution to this equation is of this form. We can have sinusoidal solutions, we can have cosinusoidal solutions. At the moment, until we apply the boundary conditions, we've got two arbitrary coefficients here. And this is one way of writing a completely general solution to that equation. Now, how are we going to figure out what A and B are? They're constants in this general solution. And we know that for these to be solutions, incidentally, K has to be the square root of 2me over h bar squared. That's a requirement on sines and cosines to be a solution here of this equation. Well, the boundary condition that the wave function has to hit 0 on this wall means that b has to equal 0. Because at z equals 0 here, this argument in the cosine will be 0, and cosine of 0 is 1. So we can't have any finite value of b. Of course, the sine is 0 at z equals 0. So if we have any finite value of b here, we're going to get something on the right-hand side that is not 0 at z equals 0. So therefore, b has to equal 0. Now, we've simplified our solution then by applying that one boundary condition, so that psi of z now has to equal a sine kz, and we're going to figure out a value for a. Now we're going to use this condition, that psi of Lz also has to be 0. That means that k times z has to be a multiple, an integer multiple of pi, because that's what will give us sine of kz equal to 0. So k, which we know has to be the square root of 2me over h bar squared, also has to be n times pi over Lz, so that k times Lz will be some multiple of pi. And n has to be an integer here, of course. So, since we know from this expression here that E is equal to h bar squared k squared over 2m, and we've just figured out what the allowed values of k have to be, then the solutions to this equation are, we put in those allowed values of k into our a sine kz, and our energies here have to be the ones where k takes one of these values. So these are our solutions. We have a specific set of energies. For each choice of n, there's another energy we get, and for each choice of n, there's another wave function that we get. So there will be a first energy corresponding to n equals 1. We'll call that E1. And here's the sinusoidal wave function that corresponds to that. It's just pi z over Lz. So when z is equal to Lz, this is sine of pi, which goes back down to 0. Here's the second one with n equals 2. Note that if we thought of this as 1 unit of energy, this is now 4 units of energy. And it will have a wave function that goes up and down and back again, because it will now be 2 pi z over Lz that we have in here. And if we put n equals 3, we'll get another possible value of energy. And note that if this is 1 unit, this one is 9 units, because it's 3 squared that comes in here. And this wave function will go up and down and up and back again, because now it is sine 3 pi z over Lz. Now, let's look a little bit at this wave function here. We can deduce something about these values n beyond what we've said so far. We can restrict n to being only a positive integer, not 0, but starting at 1, 2, and so on, for the following reasons. Sine of minus a is just equal to minus sine of a for any real number a in here. So wave functions with negative n are essentially the same as those with positive n. We would just end up multiplying by minus 1 out the front here, and this factor is already so far an arbitrary number, certainly arbitrary within a unit phase factor. So a wave function with n as a negative number is really the same solution as a wave function with n as a positive number. And of course the eigenenergy would also be the same, since it's proportional to n squared. So we don't need to think about negative values of n. They would just be the same as these solutions we've already figured out here for positive values of n. So we won't think about negative values of n. And if we chose n equals 0, well, the result is trivial. The wave function is simply 0 everywhere, and that doesn't correspond to anything physical. So we will throw that away. The particle would not be anywhere in that case. So as a result, we don't need to consider negative values of n, and we don't need to consider n equals 0. So this integer n is going to be only a positive integer. It's not 0. Now, we can normalize these wave functions. We figured out how to do that in principle, so let's do it in practice here. Here is the integral that we have to perform. And if you perform this integral, you'll see that sine squared over any complete number of half periods just gives us an average answer of a half. And so this integral turns into mod an squared times Lz over 2. Now, to have this integral equal 1, let's choose mod of an equal to the square root of 2 over Lz. Then all this on the right will turn into 1. Note that an can be complex, and all such solutions are arbitrary within a unit complex factor. But conventionally, we are just going to choose an as real and positive for simplicity in writing, though we remember we could always multiply by some unit complex factor and still get the same normalization. So to summarize then, here are the solutions of the particle in a box problem. We have a set of possible values of energy here that are spaced quadratically with n. We have a set of wave functions. These are normalized versions. They're sine n pi z over Lz with this constant out front. As with any such solution of one of these equations, we could multiply by any unit complex factor out the front here. And n is restricted to being 1, 2, 3, and so on through all the positive integers.